single grain of red dust sits on a glove seam. It's smaller than a fleck of flour, and it's about to become the most dangerous object on Mars. Nobody feels it. It just rides along in total silence. Mars looks like the most obvious danger in the entire solar system. Every rover photo shows the same rust haze hanging over rust-colored ground. Radiation gets blamed for that. So does the cold, and so does the airless vacuum. Those threats are real, but they're not the one climbing NASA's list right now. The real danger is the dust itself, the exact thing coding every photo, and it gets in through the one object every astronaut trusts completely: the suit. Here's the real puzzle. Apollo astronauts already walked through lunar dust, decades before Mars was on the table. They came home fine, more or less. So why treat Martian dust as something genuinely categorically new? What could possibly be silent about a hazard you can literally see coating every surface? It shows up in nearly every photograph Mars has ever sent back to Earth. Why would the suit meant to keep you alive let this exact danger through? Here's the answer. The silent killer waiting inside every Mars suit is the planet's own dust. It's fine enough to slip past mechanical seals engineers spent years perfecting. It's toxic enough to cross straight into the bloodstream, once fully inhaled. It's persistent enough that NASA wrote an entirely new safety standard for it. That standard became official binding policy in 2026. Now zoom all the way in, down to the single grain itself. An average Martian dust particle measures about 3 micrometers across. That's roughly 4% the width of a single human hair. Something this small simply doesn't behave like ordinary sand at all. It doesn't fall quickly the way coarse terrestrial dust falls on Earth. Instead, it floats, suspended in the thin Martian air for hours at a stretch. It slides straight past the nose and throat without meeting any resistance. Those are the two natural filters your body relies on most heavily. So instead, it travels down into the deepest branches of the lungs. Those branches are called alveoli, the tiny sacs where oxygen actually enters blood. Damage there doesn't heal the way skin or muscle tissue does. Once alveoli scar over, that lost capacity generally never comes back. There's a second problem too. Iron oxide is the mineral that paints Mars its famous rust-red color. That same iron oxide happens to carry an electrostatic charge as well. The dust doesn't just settle onto a surface and quietly stay put. It clings. It clings to fabric, to boots, and to every joint on a suit. Lunar dust clung to Apollo hardware the exact same way, decades earlier. Static builds as grains rub against each other in the thin, dry Martian wind. Once charged, those grains actively pull toward any surface with an opposite charge. A spacesuit, covered in exposed metal and fabric, is exactly that kind of surface. Curiosity and Perseverance have measured this exact chemistry directly, grain by grain on Mars. Perchlorate salts sit inside it at 0.5% to 1% by weight. Silica and gypsum turn up in the same rover samples, alongside trace heavy metals. Chromium and manganese both appear in small but measurable concentrations. Mars has essentially no rainfall and almost no wind erosion cycle to soften anything. So individual grains stay jagged and abrasive, almost indefinitely, unlike dust on Earth. For years, people treated Martian dust like ordinary beach sand, something you brush off your boots at the door and simply forget about. That casual idea made sense back when radiation dominated every conversation about Mars risk. NASA's own 2026 engineering standard now says otherwise entirely. It treats dust as a first-order hazard, not a housekeeping nuisance. It sits in the very same category as radiation dose limits do. How did sand become a binding standard? Go back to the Apollo missions first, decades before any of this. Apollo astronauts came home from the lunar surface sneezing uncontrollably. Their eyes watered, their throats burned with an irritation nobody had fully anticipated before launch. Lunar dust had worked its way into their A7L suits during every single moonwalk. It drifted into the lunar module cabin the moment helmets came off. Some crew members described the smell as sharp, almost like spent gunpowder. That detail told scientists the dust was chemically active, not inert. NASA documented every symptom across every astronaut and mission. Investigators went looking for the mechanism itself. Lunar regolith had never been softened by wind or water erosion. Its microscopic edges stayed razor-sharp across billions of years untouched. Those sharp edges abraded spacesuit boots with every single step taken. They tore straight through the vacuum seals on sample containers. Some samples were contaminated before they ever reached a lab bench on Earth, so dust wasn't just a cosmetic annoyance you could wipe away. It was quietly degrading the exact hardware meant to protect astronauts. Engineers took that lesson seriously when they began designing Mars-bound systems. Different proof arrived in 2018. Stony Brook University ran a very different kind of experiment entirely. Biochemist Bruce Dempel and his team led the published study. They exposed cultured human lung cells to lunar soil simulant directly. This was lunar dust, not Martian dust, tested years before Mars missions were planned. They exposed mouse neurons to that same simulant too. The result was stark. Up to 90% of those exposed cells died outright. This wasn't a story about torn seals or scratched boots anymore. It was a biological finding, built on cellular toxicology. No equivalent published study has yet run the same test with real Martian dust. Dust could wreck hardware and kill cells. Mars escalates both of those separate problems at the exact same time. Martian dust averages 3 micrometers across. Remember that number. Lunar dust ran considerably coarser than that, by direct comparison. Finer particles penetrate much deeper into fragile human lung tissue. Finer particles also stay suspended far longer in enclosed habitat air. They also carry a larger surface area relative to their tiny mass. More surface area means more chemically reactive contact with living tissue. Every single problem the Apollo crews reported gets sharper here on Mars, not milder, sharper. It travels deeper, it lingers longer. Now add the chemistry rovers have already measured directly on the ground. Perchlorate sits inside that dust at up to 1% by weight. Perchlorate interferes with thyroid hormone regulation in the human body. It does that the moment it crosses into the bloodstream through lung tissue. The thyroid regulates metabolism and cognitive sharpness alike. A few milligrams of inhaled Martian dust can exceed the safe daily perchlorate dose. Not grams of dust, milligrams. That's the entire gap between a safe breath and an unsafe one. And the iron oxide isn't finished yet either. That same red pigment is the exact source of the static charge. It's the identical mechanism documented decades earlier during the lunar missions. It clings to fabric and seals through static attraction alone, constantly. Suit joints flex constantly, which only helps trap grains deeper into the weave, so a walk outside isn't a chance of dust transfer. The static charge makes that transfer happen automatically. Every time a suit touches dust, every excursion becomes an event that carries dust straight back home. Now stack one more layer on top. Astronauts already face elevated pulmonary risk purely from cosmic radiation exposure. That radiation accumulates during the long transit through deep space. Their lungs arrive at Mars already partly compromised before landing even happens. Now layer toxic, ultra-fine dust onto that already weakened tissue. The two risks don't simply add together in some tidy, predictable way. They compound each other instead, in ways neither would alone. That interaction could accelerate lung disease and meaningfully elevate cancer risk. Here's the honest limit, though. Nobody has measured that exact combined effect yet. No human has ever breathed Martian dust while carrying deep space radiation damage, so the compounding risk is a documented concern, not a confirmed number. Go back to how NASA actually set its safety numbers in the first place. For years, NASA's working number came straight from the moon. The lunar limit was a 30-day permissible exposure standard. It sat at 0.4 milligrams per cubic meter of air. For a long stretch, that was the working assumption for Mars too. Treat Martian dust the same way lunar dust had already been treated. Both are just fine planetary regolith drifting through a sealed habitat. That assumption didn't survive the actual chemistry. In February 2026, NASA convened a Martian dust limit working group. Toxicologists David Damby, Claire Horwell, and Joyce Tsuji joined the review. NASA's own Elizabeth Rampey and Torin McCoy worked alongside them closely. Their conclusion was blunt. The lunar number simply wasn't conservative enough for Mars conditions. Mars dust carries higher iron content and unknown amorphous mineral components. So they set a new standard, 3 times stricter than the old one, 0.1 milligrams per cubic meter, over any rolling 24 hours. That's a dramatically tighter margin than anything Apollo crews ever had to consider. It's now written directly into NASA STD 3001 Volume 2 as binding policy. That group named the exact moment danger peaks. It isn't during the walk outside itself, out on open ground. It's the moment right after, stepping back through the airlock door. Dust concentration spikes precisely at that specific transition point. The suit itself is the vector carrying the hazard indoors, not the storm rolling across the horizon somewhere in the distance, not the exposed ground underfoot either. The suit an astronaut just spent hours trusting completely with their life. That's the exact object physically bringing the danger back home. So what can be done about it? Engineers are already testing possible fixes, though none is finished yet. Self-cleaning suit fabrics are one approach under active lab testing. Some use coatings designed to weaken the exact static bond that causes clinging. Electrostatic repulsion devices are a separate idea, still in early prototypes. They'd shake dust loose from a suit right before the airlock door opens. Neither one exists as flight-ready hardware for any scheduled mission yet. So for right now, this stays an unsolved engineering problem, not a contained one. Step back and look at what this actually means, day to day. Picture tracking fine construction site dust into your house on your shoes. That happens after spending just one afternoon outside in it. Except this particular dust carries a mild thyroid-disrupting chemical inside every grain. It's small enough to drift through your rooms for days on end. And you can never shut off the air filter to clean it, because that filter is also the only oxygen supply you have. That's the exact situation NASA is now fixing. The shoes are the spacesuit, the house is the Mars habitat itself, and the dust doesn't stop arriving until the mission is finally over. So bring the whole picture into one single frame now. Apollo-proved dust could wreck hardware and irritate human tissue. A lunar dust lab study showed it could kill cells outright. Mars took every one of those threats and made each one worse. Finer particles, deeper penetration, confirmed thyroid-disrupting chemistry, lungs already weakened by radiation before the dust even arrives. The old lunar safety number couldn't survive that accumulated math. So a named panel rewrote it in 2026, 3 times stricter, and they pointed straight at the airlock as the moment of peak risk. For decades, astronauts trained to fight the dramatic dangers, radiation storms, equipment failure, the vacuum of space itself, waiting past a single torn seam. Those are the threats every training simulation gets built around. The boring stuff might be hardest of all. You can't shoot dust down out of the sky. You can't shield against it the way you shield against radiation. You can't simply avoid it either. Avoiding it would mean never stepping outside the habitat at all. It rides in on the suit every time the airlock opens. Picture that same thin reddish film once more. It's caught in the seam of a glove. It's invisible until backlit by a work light. Ordinary looking under any light you'd choose to examine it. And yet it's the one hazard on Mars that never stays outside. It follows the astronaut home every single time.